Thank you very much. Can you guys hear me? How's it going, everyone? Enjoying the conference? Excellent. So my name is Hany Fahim. I'm the founder and CEO of VM Farms. I've been wrangling servers for the better part of my life, seeing many different things in the field of operations. So I'm actually continuing a series of talks called Tales from the Ops Side. This particular talk is called Earthquakes in the Moon, and it's about I usually like to tell some stories about things that we've seen in the field. So I'm going to jump right into it. Do you guys remember where you were on June 30th, 2012 at about 8 p.m. Eastern Time? If not, I definitely do. That day will forever be burned into my memory. I was at home. It was a Saturday. It was glorious, bright, sunny summer day. I was just finishing up dinner, and I was doing the dishes. This is before I had a dishwasher. And all of a sudden, disaster struck. We had multiple site outages reported, and so I run a hosting company. So all these site outages all of a sudden at the exact same time. My first thought, by having so many outages, was maybe it was a network outage. But the servers were accessible at the time, so it couldn't really have been the network. So then the next thought was maybe we're under attack. Maybe there's some sort of DDoS happening at the time. But maybe. It wasn't really obvious at the time. Then, shortly after, we started receiving a whole bunch of server load alerts, and they were piling up from all over the cluster. Things weren't really making any sense. Didn't really understand what was going on here. There's so many questions that were unanswered. You know, why all at the exact same time? It was very strange. And what was the pattern that was inherent here? Upon closer inspection, it appeared that it was only certain processes that were impacted by this and responsible for all the system load that we're seeing. MySQL was definitely one of them. Java and Ruby-based apps were also impacted, which didn't make any sense whatsoever. These are completely different systems, but somehow they all were contributing to high load. So putting on my ops hat, I pulled out my trusty strace tool. I love this tool. It's one of my favorite. So basically, strace, if you don't know, it watches system calls to the kernel. So anytime you want to access a file, or in this case, get the time of day, you can use strace and it'll tell you what was going on. So attached to one of these misbehaving processes, and it didn't make any sense. It was just constantly asking for the time of day, get time of day, get time of day, over and over again, attached to a different one. So this was MySQL. I switched to a Java process, did the same thing, asking for the time of day over and over and over again. It didn't really make any sense. So why were these asking for the time? Was there some maybe crazy time event that we didn't know about? So popped up Google and did a quick search for time event, and it revealed the answer right then and there. On June 30th, 2012, at 23:59:60 UTC, a leap second was inserted into the clocks all around the world at the same time. At midnight UTC equals 8 p.m. Eastern Time. All right, figured it out. Now we knew what was going on. Now what? Things are still down and didn't make any sense. So what is this leap second, and how do we fix it? Why is it broken to begin with? But you know what? Our goal at the time was to just stabilize the cluster. So we started trying to do things like restarting the processes, trying to see if that'll fix it. And for the most part, it kind of worked. You know, restarting processes kind of worked, but sometimes an entire reboot was necessary to kind of bring things down. So after doing this, we spread out to the rest of the team and told everyone, you take a piece of the cluster and let's start rebooting these servers if necessary. And within an hour, things had calmed down. Okay, what just happened there? Didn't make any sense whatsoever. Doing some quick research online, it turned out that we were actually not even alone in this. Qantas Airlines, they suffered massive delays in their kiosks due to this leap second over here. And there are many, many other stories on the internet about this specific date which blew up. So Reddit, Foursquare, Mozilla, Gawker, LinkedIn, StumbleUpon, Yelp, and these are just to name a few. All of them blew up. It was kind of reassuring to know that at the exact same time, all around the world, people's pagers were going off. So we were not the only ones. So what is this leap second? Up until this time, I actually had no idea what a leap second was. Leap second, apparently 25 of them before this time had been inserted into the clock since 1972. So it didn't make any sense why this particular one in 2012 was so special. And the answer, obviously, like everything else in life, is extremely complicated. So you kind of have to take a step back for a second and figure out why is timekeeping so incredibly important. So if you think about it, time is the universal frame of reference for everything. Across every single programming language that you've ever touched, at some point you're going to deal with time. It's the only way that we can get to work relatively at the same time. And in modern day, high resolution timekeeping is extremely essential. So if any of you run high traffic websites, you know what I'm talking about. If you're trying to correlate some events and you're having hundreds of requests a second, and they're all happening at the exact same second because your timestamp only has a resolution of a second, it's really hard to figure out what's going on from there. Atomic clocks, satellites, and even celestial bodies are used and consulted to make sure that we're all on the same clock. So just taking a step back, brief history of time. You guys know about Greenwich Mean Time. People have heard about that, I'm sure. It was the first widely adopted time standard that everyone kind of adopted at the time. It keeps track of something called the mean solar time, and we know that as a day. And mean solar time is actually kind of interesting. It's not one rotation of the Earth, because if you think about it, a day is actually, the Earth is orbiting around the sun. So a day is actually, you're moving in your orbit, so it's actually the time when the sun arrives at the exact same spot. So it's a little bit more than 360 degrees. But it's mean time because of the wobble of the Earth and many other factors. The sun actually does not stay still. So they call it the mean solar time. But it's not enough to do that, because I'm going to get into the reasons for that. It's not enough. There are actually too many variations in here. So the scientists and the powers that be created a new standard called the TAI, which is time based on atomic clocks. TAI stands for International Atomic Time. It's all reversed because the French people apparently wanted it that way. Atomic clocks are most of them are based on the cesium-133. So it's measuring the jump in the electrons in their state in there. And after a certain amount of frequency jumps, they calculate that as a second. So it's extremely, extremely precise. But that's not, the Earth is an ever-changing body. So they also created two other time standards to make things more complicated. They created UT1 and UT0, and these are time that is based on the exact measurement of the rotation of the Earth. And this is ever-changing. So you have atomic clocks, which never change, are always precise, and then you have UT0 and 1, which are always changing because the Earth is not a static body. So they invented something called Coordinated Universal Time, or UTC. It's basically atomic clocks, but with leap seconds inserted to kind of keep it in sync with UT0 and UT1. And then you have GPS, and they're in their own little world there. They're also based on atomic clocks, but they're separate from everybody else. I think at this point they're 17 seconds ahead of UTC. So there's a lot of complication over here. Did you guys know that our days are actually getting longer? You know how people say, I wish there's more hours in the day? It's actually happening, but it's not really measurable to us here. The Earth's rotation is actually slowing down over time. So a day today is about 1.7 milliseconds longer than it was 100 years ago. So why is that? Well, I have my awesome diagram over here. It's actually because of the moon. The moon is actually tugging on the Earth, and vice versa. We're actually tugging on the moon as well. There's tidal forces that cause a drag force on the Earth, which pushes the moon further away from us and actually slows down. So if you can imagine, that's why we have tides. But not only tides move it, it's actually also the crust of the Earth. As the moon kind of tugs away at that, the Earth bulges towards it. So in my diagram over here, the part that is facing the moon is actually closer and is being bulged that way. As it rotates away, the moon kind of tugs on that bulge a little bit further because of gravitational forces and slows down the Earth. We actually did the same thing to the moon, and that's why the moon always looks the same no matter what time of year it is. It's always facing to us. It's something called tidal lock. So tidal lock is because it's not that the moon is not rotating, it's in perfect synchronous orbit with its orbit around the Earth. So it's always facing us in the same direction as it kind of spins around. And we did that to the moon, and the moon is doing that to us, although a lot slower than that. But the Earth can actually speed up as well. So to add more complication, it's obviously a living being. So major events like earthquakes can also affect the rotation of the Earth. So if you remember Boxing Day 2004, there was a massive 9.1 magnitude earthquake, and it struck in the Indian Ocean off the coast of Indonesia. Here's like an example of how the tsunami kind of propagated across the ocean over there. It was so massive. This force was so great that it actually changed the moment of inertia of the Earth, and a day was actually now 3 microseconds shorter, just like that under one event. In 2011, a 9.0 magnitude earthquake struck Japan, and in this case over here, the day was shorter by 1.26 microseconds. So it may seem really small, but if you're these guys that are measuring the time like UT0 and 1, this actually matters all the time. So you're always watching this clock over here. So basically to say time does not sit still. So to compensate for these irregularities, the powers that be, they invented something called the leap seconds in 1972. So there's this body called the International Earth Rotation and Reference System Service, IERS. They're actually in charge of scheduling these leap seconds. And they are not predictable. So this is where a lot of controversy comes in. Because it's not predictable, they can't give you a schedule and say, here's all the leap seconds that are coming for the next 100 years. They actually only announce it about 6 months ahead of the, that would be bad, 6 months ahead of time for that. So it actually, you only get 6 months to prepare for a leap second, which usually would not be the case, but apparently in 2012 things blew up. So here's a diagram of all the leap seconds that occurred, and you can see the diagram over here is about the drift according to the Earth's rotation based against the atomic clocks. And you can see every time the vertical jump over there, that's actually a leap second that's occurring, that's trying to reset the clock. You can see between roughly, 1999 to about 2006, the Earth actually did not slow down as quickly as it thought. So that's why there's that big lull period over there. And then it kind of came back to regularity. And that red line over there is the most recent leap second that we have. It's very irregular, and there's probably 1,000 reasons why it looks irregular like this because of all the events that happen on the Earth. But it's too hard to calculate. So they say 6 months in advance they're going to announce this. So now we dig a little deeper. We get back to Linux and the leap second. So Linux does not have a concept of a leap second. More specifically, POSIX, the POSIX standard does not have a concept of a leap second. There are 86,400 seconds in a day, period. No change to that. So to compensate for this, because obviously they have to do that, otherwise they'll be off, what they do is repeat the last second of the day. So if you're trying to catch your clock, you'll never see it go to 60 seconds. It'll always be 59, but it just repeats that second at the very end. And this requires that all systems keep up to date with the latest announcements. And the only way to do that in Linux is through NTP. If you guys are not running NTP on your systems, you're probably out of drift right now. So in preparations for this talk, I actually tried to demonstrate what a leap second would look like, but you wouldn't believe how difficult it is to do that. It's not enough to just rewind your system clock to June 30th and wait for it to happen. It actually doesn't do that. It depends solely on NTP. And NTP is this massive network around the globe. And it's actually very well secured. So I tried to see, all right, I want to reproduce this. I want to do this for this demo over here. So the first thing I had to do is create my own NTP ecosystem. I had to cut myself off from the entire internet because obviously NTP is meant to keep you on time and not to skew the time. So I had to create my own ecosystem there. But then Hany inserted a leap second into there, and apparently there's this distributed, you can actually see it online, there's a distributed text file that is with a signature on there that every NTP server is supposed to read and distribute and set a flag for Linux servers. So I tried to muck around with it and set a new leap second in there. And because it's a signed document, I actually couldn't do it. I had to hack the NTP code in order to override some of the security settings in there. Because if you can imagine somebody getting a hold of this file over here, they can screw every system on the planet. So I actually gave up after a couple of hours. It was not feasible. I'm not really a C programmer, and it was a little bit over my head. So I could not demonstrate it, but believe me, that's the only way that it happens. So again, why did things break in 2012? It didn't really make any sense. So I had to do a little bit more digging to figure this out. So Linux has this concept of a high-resolution timer. They call it the HR timer. And it is used for timing events. So you guys writing code, if you put something like a sleep command in your system, it relies on the HR timer to wake up whenever it does that. And all kind of timing events rely on this HR timer. So many applications like MySQL or Java, or Ruby, they rely very heavily on this HR timer. And they do it for things like loops. During 2012, this leap second that was introduced, this HR timer, for some reason, kept moving forward while the rest of the system repeated the last second of the day. So just demonstrate this over here. You have this last second of the day, UTC, 11:59:59. You have the system clock, and you have this HR timer over here that they're perfectly in sync with each other. Well, the leap second occurs, right? So the system clock holds itself back. It repeats the 59 second, but the HR timer just kept moving forward. Okay, why did things break though? Well, if you can imagine, you have this loop. Let's say you sleep for something less than a second, okay? So let's say you sleep for half a second over here. You set the timer with the HR timer and you say, I want to sleep for half a second. So technically, you want to sleep the timer for 0.5 UTC. Well, because it's already ahead of the game over there, it immediately returns back to you and says, hey, you're late. It's actually 1 second past UTC. You're late in your timing, so here you go. You got to fire your event. But because it didn't actually sleep, it returns and says again, hey, I need to sleep for another, less than half a second. So it gets locked in this endless loop here where it's constantly returning back and forth and saying, hey, set a timer for half a second. It's like, it's already passed. You're half a second too late. And basically goes as fast as the CPU can possibly churn. So if you measure the temperature in your data center at the time, things probably got a little hot in there because every CPU was going mad. The fix apparently was really simple. So I mentioned back in 2012, the solution that we came up with is rebooting everything. It actually turned out to be a lot simpler than that. You just have to set the date. You set the date to the date, according to this time over here. The act of merely setting the date on the system is enough to fix it because that resets the HR timer. And this little command over here is basically it gets the date and then sets a date to itself. It's a little cryptic over there, but that's the fix. Once you do that, the HR timer now comes in sync with the system timer and everything is glorious again. But again, why did this break in 2012? It didn't make any sense. There were 24 leap seconds since 1972 before this time. Actually turned out to be a bug fix deep in the. It actually took quite some time to dig into this to figure it out. But there was a bug fix in 2007 over here. It's a little difficult to read. But this guy submitted a patch to the kernel, and he said, I found this edge case over here where on some certain circumstances when the leap second is introduced, system timers can go out of sync with the HR timer and things can blow up. So what I'm going to do is I'm going to remove this line of code over here called clock was set. This clock was set is what happens when you run that date command. It actually sets it and brings all the system timers in check with each other. So he removed it, saying that this will remove, the edge case. Linus gave it the thumbs up, merged it in about 2009, I believe. And then 2012, when the leap second came in, because it didn't run that piece of code, you had out of sync timers and the entire internet broke because of Linus. So how does Python handle this? So kind of looping in there. I mentioned Ruby, MySQL, Java that broke. Surprisingly, it didn't have, at the time in our cluster, didn't have too many Python processes breaking, but it doesn't mean that it can't. There's this issue that's opened up, 23574. It was opened up actually earlier this year in March 2015. And it was discussing, the upcoming leap second that was there. So the datetime module actually does not support leap seconds specifically. Basically says, note on non-POSIX systems that include leap seconds in their notion of a timestamp, leap seconds are ignored from the timestamp function call over there. So if you read that, it's actually quite an interesting thread. I encourage you to read it because it quickly devolved into some philosophical discussion on POSIX itself. People were making fun of POSIX, saying that it's just it's a standard designed to stop progress on the internet, and people are like, no, it's trying to get everyone on the same page. And there's some hatred for astronomers in there as well. It's actually quite a funny one. In the end, the original author basically gave up. He replied, sorry, I give up on this issue. I don't know how to fix it, nor if it's even possible to fix. So they closed the issue and marked it as won't fix. So it's still kind of pending out there. Nobody knows how to fix it in Python specifically. Surprisingly, this year, when this leap second happened in 2015, my entire team was ready for disaster again. We had that date command ready to go in case there was something wrong, and we were ready to fire it. But actually, nothing broke, not severely this time around. It's because that many apps have actually internally fixed it. They've learned their lesson from 2012 and taken it upon themselves to fix their own code to kind of work around these possible issues. We actually still did experience some issues, and these are some of the older systems that have not been patched, like most of the Java apps actually. They didn't fix it, but it wasn't a disaster. There were no site outages. There's only a few of the issues. And in fact, if you people, whoever runs systems out there, go check your graphs. If there's a high CPU since about June 30th, it's probably because there's a leap second issue. But because it's not so severe, it may go unnoticed. So go and check it and maybe set the date on your clocks. So, the quick fix, as I mentioned, that date over there, There's some groups out there that want these leap seconds abolished, and due to these problems, they're like, this is just too ridiculous. We need to find a way to another way of approaching this, but leap seconds is not going to work. Surprisingly, Google no longer uses leap seconds. So instead, what they do is they smear an entire second over the course of a year. So instead of doing it in one fell swoop in one event where system timers can get all out of sync and everything blows up, what they do instead is when there's a leap second announced, they start smearing that second. So they modify their NTP servers. And Google thinks, we're the entire world anyway, so our own NTP servers is separate. It's fine by us. So they start smearing it across the entire year. So within 12 months, it would have caught up with the rest of the world. And there's actually a lot of people who are adopting this standard as well. Red Hat, I believe, is introducing a new type of NTP protocol called Crony. And Crony actually has about 6 different ways of approaching the smear thing. It's an entire other topic, which I won't cover over here, but it's really interesting stuff. So maybe there's good news, maybe. At the end of this month, November 2015, they're discussing at the World Radio Communication Conference, or WRC, they're in Geneva, they're discussing the abolition of the leap second. There's actually, I don't expect much resolution from here because there's a lot of people in both camps. There's Australia, United States, and China. They're all about abolishing the leap second. They're like, there's too much chaos over here, too many unknowns, and they want it abolished. And then you have Britain and Russia and actually a lot of other, former satellite communist states as well, that they're all in favor of keeping it as well. But it doesn't really make any sense. Like, something has to be done because, they're calculating by the year 2700, which is way past our time, but systems will still be around. The day will be off by about 30 minutes. So when the sun comes in at about noon, it'll actually be off by 30 minutes. So something has to be done. And there's really, really no answer one way or the other. But at the end of the day, you just got to blame the moon. Any questions? That's all I got. Time? Repeat it. Will do. Absolutely. Go check your graphs. Yes?
Does relativity matter for any of this?
Relativity, in what sense? I mean, these things are moving pretty slowly, so...
You mentioned satellites.
Satellites, actually, yes. Yes, so satellites, they have the GPS, they use GPS as their own syncing time. Actually, there's an interesting story about how GPS, when they first launched the GPS network, they noticed that all the times are actually kind of out of skew with things on the Earth. And after a lot of people with heads being rolled, they actually realized it's because of relativity, because they're spinning so fast and they're beaming the coordinates and the time back down to Earth. They did not account for relativity in here. So what they do now is they compensate for that. So your GPS device on here knows about the skew and the relative speed of the satellites up there, and they just account for that on their systems. So it does matter with GPS. Yes, it's very interesting. Yeah. Lots of interesting stuff. Any other questions? Yes?
Correct me if I misunderstood this, but the bug back in 2012 that occurred in all these apps happened because they asked to sleep, and then when they woke up, they asked for the time, compared that to what they expected it to be, and asked to sleep again if it was not, and had not advanced.
Exactly. So because there's that skew in there, you say, I want to sleep for half a second. The Linux kernel, yes.
Okay, so if those applications have all been written in a style where they ask to sleep, and they just trust the system to wake them back up after an appropriate amount of time.
Yes.
They would sleep for no time, but they wouldn't have entered this loop.
They would not. And so the question was what most systems, if they just relied on their own timing, so they measured the time when they wanted to sleep, they may not have had this issue. Is that correct? So that's what a lot of people have started adopting after the 2012 fiasco. They've actually implemented their own fixes and workarounds for that, and that is one of the ways of approaching it. Instead of saying I'm going to sleep for half a second, you say I'm going to sleep for half a second, but I'm going to check the time whenever it returns back to me, and you're going to compensate for that internally. So that's why things did not blow up so badly. So not only did the bug get fixed in the Linux kernel, but because there are older systems running out there, and you cannot always rely on it clearly from here. They've worked around that by implementing these types of fixes where you just cannot trust the HR timer, so you try to work around that, which is terrible to say. I mean, you should trust your time based on the Linux kernel, because why would your app, your web app, try to implement something like NTP or anything else? You should trust it. But as this fiasco showed, time is so complicated that situations like this, it crosses boundaries. It affects all types of applications, and things that you do not foresee can blow up. So hopefully they've learned their lesson. Actually, so Linus, after he made this fix and everyone kind of called him out on that, he did a retrospective and he talked about the complications with this, and he's saying how difficult it is to actually test leap seconds. So I tried to do that myself, and I gave up after a few hours. So they've been trying to do this constantly, and because of the infrequency of leap second events, it's actually very difficult to test. So they always have to cut themselves off and create their own little micro ecosystem where they can demonstrate, the skews and try to practice these. Like it's a really, really difficult problem to solve. So where's the fix? Back in 2007, they fixed this, and it broke in 2012. I mean, that's 5 years where they put in a fix and you didn't know if it was going to fail or not. It took 5 years before it actually reared its ugly head. It's a very difficult problem to test for, which is why a lot of these systems broke in 2012. Yes?
Do you know what was the edge case they were trying to fix here?
Do I know what the edge case was that they're trying to fix? Well, it's a very long, complicated, but it was actually exactly what happened over here, where they're saying there are cases where the system timer and the HR timer can get out of sync with each other, but it's only under certain circumstances. So this function is a generic function for the NTP. You can see it's in the ntp.c file for the Linux kernel. This is the main one, but there are other calls that depend on this that the guy caught the edge case in, not probably realizing that this is probably the more fundamental part of the system that depends on it. So inside the Linux kernel, this loop was happening. So by removing this over here, it fixed the problem in the Linux kernel, but broke it for every other application and the internet at the same time. Yeah, very different. Yes, in the back there.
You mentioned that the quick fix for you guys was to set the date to the date of the kernel, right?
Yes, the date to the date.
I'm guessing that's going to set the HR timers.
Yes, it actually just runs that. Well, amongst other things, it runs that function, the clock was set function.
When the NTP, like when NTP updates or syncs with your time, right? Wouldn't that also execute the same date?
If you left it alone for enough time, because NTP does not immediately fix it. It does everything very, very gradually in order to not break things. So if you just left it alone for a long period of time, it may have done that. But you need to realize that when the things are caught in a loop, in an endless loop that way, it's very hard to break out of that loop. So many systems like MySQL completely froze because they're just endlessly catching up in here. So even if the time kind of eventually skewed over there, it will take a very long time for it to break out of that loop. So you have to, when you run that command, it basically fixes the timer and all of a sudden it returns at the normal time it's supposed to. I think when you skew it off by second, depending on your settings, it can actually take like weeks for it to finally get exactly in time and break out of this loop here.
I guess by restarting the server, you're restarting the NTP data and then...
Exactly. You're resetting with a sledgehammer. You're basically resetting the clock over there, because that's the first thing that it does is it sets the time over there when the kernel boots, and then everything is in sync with each other. That's why it worked in 2012. But really, you just had to set the time and just basically call this function over here in the kernel.
And on that note, that's the conclusion of...
Thank you.